Alright, in this video I want to talk about the magnetic field of a line of current. Now before talking about the magnetic field of a whole current, we're going to talk about the magnetic field of a current segment. So that's a small segment in a wire that carries a current I. And we're interested in the magnetic field at a point P in space, and we're going to call delta B the magnetic field at a point P due to the amount of charge delta Q that is contained in that segment that you see there, delta S, but that amount of charge delta Q is the amount of charge that passed a reference line. So we're going to have a little guy here counting the charge that passes through a particular reference line in a certain amount of time, delta T. Okay, so that amount of charge, we're going to call it delta Q. So we know what the magnetic field is produced by a point charge. A point charge with an amount delta Q produces a magnetic field in space at a distance r in a particular direction determined by r hat. If the charge is moved with velocity v, then this is the amount, the equation that we saw before. Biot-Savart equation tells us how much is the magnetic field. Remember that this segment contains all the charge delta Q that was able to pass through the reference line in an amount of time delta T. So again, this velocity actually is the drift velocity. That drift velocity is the velocity that each one of these charges has. So if this is a wire, the charges that we're talking about are electrons, and those electrons are moving inside the wire with a velocity that we call the drift velocity. Okay, so in this equation now we can also make use of the fact that, as we said before, delta Q is the total amount of charge that was able to pass through a reference line in a certain amount of time delta T. So using the definition of current, current is the amount of charge in a certain amount of time delta T, amount of charge divided by time. Then the amount of charge that we're talking about can be written as the current in the wire multiplied by delta T. So that's one replacement that we can do in this equation for delta B. The other replacement that we can do is that the velocity at which those charges are moving inside the wire can be written also in terms of the distance they travel in the amount of time delta T that it took to travel that distance. So if we replace both of those equations, delta Q as the current multiplied by the delta T, and we replace Vd, the drift velocity of the electrons, as delta S over delta T, we can write this equation, the delta B equation, substituting delta Q and substituting the velocity, the drift velocity. You can see that the delta T cancels, and we get this equation that tells us what is the magnetic field of a segment of a wire that carries a current I. So this equation is now put in terms of the vector delta S that specifies the length and the direction of the segment, and the vector r hat, which tells us the distance from the current segment to the point P in space that where we're measuring the magnetic field. So this is the Biot-Savart equation for a current segment. Previously we had talked about the Biot-Savart law for a point charge. Now, using the Biot-Savart law for a current segment, we could calculate the magnetic field of a wire that carries a current, because every segment, delta S, in which we can divide a current carrying wire would produce a magnetic field given by the equation that we just derived. So the net magnetic field produced by the whole wire is going to be the sum of the contributions due to every section of the wire. So let's suppose that we have some curvy wire somewhere in space, and we're wondering about what's the magnetic field at a particular location produced by the current in this wire. So what we're going to do is, as we've done before, is divide the wire into segments. So let's say that we take the first segment and we call that delta Si is the length of that first segment, the vector delta S along the wire, and there is a position vector that goes from the segment to the point in space where we're calculating the magnetic field. I'm going to call the magnetic field produced by the segment delta S1 of the wire, I'm going to call it delta B1. So that's a vector, it points in a particular direction. There is a distance r1 between the segment delta S1 and the point in space, and the unitary vector r1 would help us determine what's the magnetic field according to Biot-Savart, and we can do that for all the segments along the wire. So we take a different segment that has a length delta S2, it's got its own r hat 2 and r2 the distance, and that one will produce or contribute to the magnetic field at that point in space with the vector delta B2. We do the same thing for all segments along the wire. Another segment with subindex n, it's indicated there with its corresponding distance vector, its corresponding contributing magnetic field delta B2, delta Bn, and the sum of all of those magnetic field vectors is what's going to give us the resulting magnetic field at a particular point in space, as an addition of the contributions from all of the segments in which we can divide the wire. So using this idea, we're going to be able to see in the next video how to, for example, calculate the magnetic field of an infinite line of current.